All right, so I want to switch gears now and talk about calculating and interpreting the chi-square test of independence. All right, and so the next chi-square test we want to do is called the chi-square test of independence. And so the last chi-square test that we did was the goodness of fit, and that was a single sample test. We were comparing data from a sample to some population value. Here we're doing something a little bit different. We want to look at the relationship between two nominal or ordinal variables and determine if those variables are related to each other or independent of each other. So we can think of it as kind of a relationship test or as a difference test. So for example, if we wanted to think of it as a relationship test, we might ask, is there a relationship between sex and the presence of an eating disorder? If we wanted to think of it as a difference test, we might say, do the sexes differ in the prevalence of eating disorders? So some other ways that you may have heard people call this test might be things like the chi-square test of association or the chi-square test for contingency tables. Both of those are used in addition to chi-square test of independence. All right, let's work through an example that involves the chi-square test of independence. Let's say that we want to know whether when you read your textbook has an impact on how well you do in a class. So students can either read their textbook before class or after class, and then we want to look to see what kind of grade they get. So do they get a high grade like an A or a B, or a low grade like a C, D, or F? And so to answer this question, we're going to take a random sample of 50 students from an intro psych class. And of those students, let's say 26 read the textbook before class and 24 read after class. And so again, we're classifying their grades as either high or low. All right, so here are data in a 2x2 or contingency table. So what we can see here, we have 20 people who read the text before lecture and got a high grade, 6 people who read the text before lecture and got a low grade, 12 people who read the text after lecture and got a high grade, and then 12 people who read the text after lecture and got a low grade. And remember, we said there were 50 people in our study total. So we want to make sure that all of our columns and our rows add up such that we have 50 people total in our sample. So 26 people total read the text before lecture, 24 read it after lecture, and we can see 26 plus 24 adds up to 50. And then we can see we had 32 people who got a high grade, 18 people who got a low grade, and that adds up to 50 as well. So all of our numbers are in the right places. All right, so now we want to pick a test, and we're interested in the association between when the students read the textbook and what kind of grade they got. And so we're going to do this chi-square test of independence. Our explanatory variable is when they read the book, either before or after class, and our response variable is their grade, either a high grade or a low grade. All right, assumptions. So we have a random sample. We took a random sample of students in the class. Independence of observations. We have no reason to believe that the students have relationships to each other. And let's assume that we have at least 5 expected cells in each of the cells of our table. And so let's assume none of our assumptions are violated to do this test. All right, now let's list our hypotheses. And for this test, our null and our alternative hypotheses are statements about populations, not samples. And so we express them the same way as we express Pearson's R, which we talked about in a previous module. And so we're going to use the Greek letter rho as the abbreviation here. So if rho is 0, that means that there's no relationship between the two variables. In other words, the two variables are independent of each other. So there's no relationship between when you read the book and your grade. The null hypothesis says, the alternative hypothesis says the opposite. It says that there is a relationship between the two variables. So rho is not equal to 0, and the two variables are not independent of each other. So in other words, there is an association between whether you read the book and before or after class and the grade that you get. All right, so now we have our hypotheses. Now we move on to our decision rule. We're going to calculate that critical value. This is the critical value of chi-squared. We use that to determine whether or not we reject that null hypothesis. Ultimately, we'll compare it to a test statistic chi-squared. And to find that critical value of chi-squared, we use that appendix table 9 in your textbook. Two pieces of information that we need. We need to know your alpha level, how willing you are to make that type 1 error, and then how many degrees of freedom the test has based on your categories. All right, so now we need to calculate our degrees of freedom. And our degrees of freedom for the chi-squared test of independence are calculated differently than the degrees of freedom for the goodness of fit test. So for the test of independence, the degrees of freedom is going to be equal to R minus 1 times C minus 1, where R is the number of rows you have in your contingency table, and C is the number of columns you have in your contingency table. So let's look first at the number of rows. Here we have 2 rows. We have the people who read the text before the lecture, and then our second row is the people who read the text after the lecture. We also have 2 columns. So we have the people who got a high grade and the people who got a low grade. And so the value of R is going to be equal to 2, and the value of C is going to be equal to 2. So now we can use that to calculate our degrees of freedom. So degrees of freedom is going to be equal to R minus 1 times C minus 1. In both cases, R and C are both equal to 2 here. So degrees of freedom is going to be equal to 2 minus 1 times 2 minus 1. We know 2 minus 1 is 1. 2 minus 1 here is going to be 1. 1 times 1 equals 1. So our degrees of freedom here is going to be equal to 1. And now we can take that degrees of freedom and our desired alpha level and use that along with appendix table 9 to find the critical value of chi-squared. All right, so we're using the same table 9 that we did for the chi-squared goodness of fit test. We're going to look for the degrees of freedom that we have in our alpha level and look where those intersect in the table to come up with our critical value of chi-squared here. All right, so our alpha level is 0.05, and we said our degrees of freedom were equal to 1. We look at where those two intersect, and we get 3.841, and that's going to be our critical value of chi-squared. All right, so now we need to calculate our chi-squared test statistic, and to do that, we need information on the observed frequency and the expected frequency for all categories of our explanatory variable. And in the example we're doing now, our explanatory variable is when people do the reading, either before class or after class. And so we're going to want to identify the observed frequency and the expected frequency for both of those categories. And then we'll actually calculate the chi-squared the same way that we did for the goodness of fit test. All right, so the observed frequency is actually just the data that we actually have related to when people do the reading. The expected frequency is how many people we would expect to get certain grades if the null hypothesis were true. And so the expected frequency is calculated a little bit differently for the chi-squared test of independence compared to the goodness of fit test. So for the expected frequency, it's going to be the number of cases in the row within that cell times the number of cases in the column with that cell divided by the total sample size that you have. And I'll go through an example and show you how we actually do this practically speaking. All right, so let's say we want to calculate the expected frequency for people who read the text before lecture and get a high grade. And so that's going to be what we would expect to be in this cell here. So our observed frequency was actually 20. But we want to know what is the expected frequency for that cell. So to determine the expected frequency, we're going to want to know the number of observations in the row corresponding to that cell times the number of observations in the column corresponding to that cell divided by the total sample size. So these are our data here. And so we have this cell here. Again, our observed frequency is that we have 20 people who got a high grade and read the text before lecture. So first of all, we want to know the total number of people in that row, and that's going to be 26. So that's what we will put right there. And then we want to know how many people are in the column that contains that cell. And we will look down here. That's the number of people with a high grade, and that's going to be 32. So we will put that here under the number of observations in the column. And then we're going to divide everything by the total sample size. We know the total sample size is 50. We know we have 50 participants in our study. And so if we multiply 26 times 32 divided by 50, we're going to get 16.64. That's the number of people that we would expect to be in this cell here, in the read the text before lecture high grade cell, if the null hypothesis was true. All right, so now we want to look at this read the text after the lecture. I'm sorry, now we want to look at this cell B. This is going to be read the text before lecture and got a low grade. So that's this cell B here. And in this cell, if we look at the number of observations in that row, that's going to be 26 again. We have 26 people there. And then the number of observations in that column, there's a total of 18 people in that column. And so we're going to do 26 times 18 divided by the total sample size, which we said was 50. And if we solve for that, we're going to get 9.36. So we have the expected frequency for cell A and the expected frequency for cell B. Okay, so we can calculate expected cell counts for cell C and cell D as well. So if we look at cell C, the row total is going to be over here is 24. The column total is going to be 32. So we're going to multiply 24 times 32, and then we divide by the total sample size of n, which is 50. And so we'll get an expected cell count for cell C of 15.36. And then finally, we can calculate an expected cell count for cell D. So cell D is going to be this one right here. So the row count for that row is 24. The column count for that column is 18. So we're going to have 24 times 18 divided by the total sample size of 50. That's going to give us an expected cell count of 8.64. All right, so in summary, these are all of our expected cell counts for cells A, B, C, and D. All right, so now it's time to calculate our chi-square test statistic. So for each of our cells, we're going to take the observed frequency minus the expected frequency and square it and divide the whole thing by the expected frequency, and then we sum that up for all the cells. So if you look here on this second row, we do this for cell A, then we do it for cell B, then we do it for cell C, then we do it for cell D, and then we add all of them up. So I'm not going to go through all of the math here, but so for example, this would be 20 would be the observed frequency for cell A. The 16.64 is the expected frequency for cell A. And then we're taking that whole thing and squaring it, and then we're dividing by the expected frequency for cell A. And so this chunk here corresponds to cell B. This chunk here corresponds to cell C. This chunk here corresponds to cell D. And so we go through and do all the math, and we'll finally get a chi-square test statistic of 3.93. All right, so now we have our chi-square test statistic, and we want to compare that to the critical value of chi-square to determine whether or not to reject the null hypothesis. So let's take a look at our decision rule to determine whether or not to reject that null hypothesis. All right, so if you remember, our decision rule, we came up with our critical value of chi-squared based on having a desired alpha level of 0.05. Our degrees of freedom was 1, and then our critical value of chi-squared was 3.841. And what we said is that 3.841 was going to be the cutoff for the common zone versus the rare zone. And so we said that if chi-squared test statistic was greater than 3.841, it would be in the rare zone and we would reject the null hypothesis. If it was less than that, though, it would be in the common zone and we would not reject the null hypothesis. Well, it turns out our test statistic is in the rare zone, barely, but it is, because it's 3.93, which is greater than 3.841. And so based on that, we say the chi-square test statistic is in the rare zone, and so we would reject the null hypothesis here. All right, so now it's time to interpret our results. So do we reject the null hypothesis? Yes. Again, we had our calculated chi-square test statistic is 3.93. The critical value of chi-square was 3.84. So since the test statistic was greater than the critical value, we did reject our null hypothesis. And so remember, our null hypothesis talked about whether or not there was a relationship between when a student read the textbook and what grade they got in the class. And so the null said there was no relationship between those two. And so we're rejecting that. And so what that means is that there is a relationship between when a student reads the text and what grade they get in the class. Another way that we could word it is that we could say among those students who get high grades, there's a statistically significant difference between the students who read the text before class versus those who read the text after class. Each of those is okay as an interpretation. All right, so now what's the direction of the difference? So if we go back and look at our data, we'll see that 20 of the 26 students who read before class got high grades compared to only 12 of the 24 students that read after class. So that means we got 76% of the students who read before got good grades and only 50% of those who read after got good grades. And so what this means is that completing the reading before class leads to a better grade outcome than completing the reading after class. All right, so let's put our results in APA format now. So first of all, we have the chi-square. We indicate that we did a chi-square test. We have the degrees of freedom in parentheses. Here it was 1. N equals 50 tells you the sample size. The 3.93 is the value of our chi-square test statistic. The 0.05 tells you the alpha level. So we have less than a 5% chance of making a type 1 error. And p less than 0.05 is letting us know that the null hypothesis was rejected. All right, and then one other component of the results that's worth noting is that we want to know how big the effect is. And so to determine this, we transform our chi-square value into something called Cramer's V. And Cramer's V requires a lot of calculations that I won't require you to calculate, but you will need to know how to interpret Cramer's V if I give it to you. So in this example, let's assume that Cramer's V is 0.28. Okay, so in order to interpret effect size in this chi-square test, we base it on both the value of Cramer's V as well as the number of degrees of freedom. So for example, we have degrees of freedom equal to 1. You need a Cramer's V of 0.10 to be a small effect size. It needs to be at least 0.30 to be a medium effect size. And then it needs to be at least 0.50 to be a large effect size. And we can see differences in this as we increase the number of degrees in freedom. In general, the more degrees of freedom we have, the lower the threshold is for what constitutes a small, medium, or large effect size. So in our example, we had a degrees of freedom equal to 1, and we had an effect size of 0.28. And so it doesn't quite meet the threshold for a medium effect size. We would consider that to be a small effect size.